Section 1. In early 1942, the Allied war effort in the China-Burma-India Theater collided with a geographical ultimatum that defied every established rule of military logistics. The Empire of Japan had successfully severed the Burma Road, the sole remaining artery feeding the Chinese resistance. In an instant, an entire theater of war became effectively landlocked, separated from Allied supply depots in India by the most formidable physical barrier on Earth, the Himalayas. The strategic calculation was brutal and seemingly impossible. To keep the Chinese army in the fight, planners estimated they needed to move 10,000 tons of material a month over jagged peaks reaching 20,000 feet, through the most violent weather patterns in the world, without a single road, railway track, or navigable river. Now, let's open the operational records and analyze the systems that defined this campaign. To understand the gravity of this crisis, we must first look at the map through the eyes of a logistics officer in 1942. Traditional military doctrine relies on the efficiency of surface friction, steel wheels on rails, or rubber tires on pavement to move mass tonnage. When the Japanese army captured Rangoon and cut the Burma Road, they didn't just win a tactical victory. They achieved a total logistical strangulation. China was, for all strategic purposes, an island surrounded by land. The Japanese strategy was one of asphyxiation, predicated on the assumption that no modern army could survive without a terrestrial supply line. This assumption was historically sound. At this point in the war, air transport was viewed as an auxiliary luxury, suitable for moving VIPs, urgent mail, or perhaps a few crates of critical medical supplies. It was not a pipeline. The concept of sustaining an entire nation's war effort solely through an air bridge was a logistical heresy. The math simply didn't work. The fuel required to lift cargo over the Himalayas, a route pilots grimly christened the Hump, threatened to exceed the payload itself. When we analyze the situation facing Allied planners, we see a logistical vacuum. There was no infrastructure to support the demand. The distances involved meant that any aircraft attempting the crossing would be operating at the absolute limit of its range and ceiling, navigating blind through monsoon storms and icing conditions that could snap a wing spar in seconds. Yet, the strategic cost of inaction was too high. If the supply line failed, China would collapse, freeing nearly 1 million Japanese troops to redeploy against American forces in the Pacific. The Allies were forced to attempt the impossible, inventing strategic air logistics from scratch in the most hostile environment on the planet. They needed to turn the sky into a highway. But to do so, they first had to overcome the reality that the technology to sustain such a massive throughput did not technically exist. Section 2. The Allied response to this geographical blockade was the creation of the Air Transport Command's India-China Division, a logistical entity tasked with executing the first strategic air bridge in history. The operational plan was audacious in its simplicity, but staggering in its complexity. If the mountains could not be crossed by road, they would be leveled by altitude. The objective was to establish a continuous aerial conveyor belt and aluminum trail connecting the tea plantations of Assam, India, to the dusty airstrips of Kunming, China. However, when we examine the initial operational architecture, we see a plan built on desperation rather than established doctrine. The logistical model assumed that aircraft could function like trucks, running high-frequency sorties with minimal turnaround times. The goal was to reach that target of 10,000 tons per month, delivering gasoline, munitions, and spare parts to sustain the Chinese Nationalist Army and the American volunteer groups operating in the theater. But this target revealed a critical flaw in the planners' initial calculations. They had focused entirely on the flight without fully respecting the ground. The system's primary bottleneck, paradoxically, was not the Himalayas themselves, but the supply chain leading to the airfields. To get a single drum of aviation fuel to a plane in Assam, it had to travel thousands of miles by sea to Calcutta, then transfer to a slow river barge system, and finally endure the Assam-Bengal Railway. This railway was a single-track, meter-gauge line that was never designed for heavy military freight. It became a constriction point, where modern demand collided with antiquated infrastructure. We see here a classic failure of end-to-end integration. The capacity of the airbridge was irrelevant if the terrestrial feed line was choked. Furthermore, the initial plan suffered from a severe standardization crisis. The early fleet was a ragtag collection of converted commercial airliners and bombers, DC-2 seconds, C-53 seconds, and even repurposed B-24 seconds. Each airframe had different performance characteristics, different cargo capacities, and, most disastrously for a remote supply chain, different spare part requirements. The maintenance depots in India became nightmares of logistical complexity. Mechanics were forced to cannibalize one aircraft to keep another flying, creating a hollow force where the number of aircraft on paper did not match the number of aircraft on the flight line. The operational tempo demanded by the plan also ignored the realities of the environment. Planners assumed standard commercial flight hours, but the hump was an operational theater where the jet stream could blow a plane backward and icing could coat wings in minutes. The attrition rate was not just a result of enemy action. It was a systemic byproduct of pushing unsuited machines beyond their design limits. The airbridge was functioning, but barely. It was leaking tonnage through inefficiency and accidents. To turn this desperate gamble into a sustainable supply chain, the Allies needed to stop improvising. They needed to standardize the system around a single platform that could survive the punishment of the route while simplifying the chaotic maintenance demands. They needed a machine that prioritized reliability over raw performance. Section 3. Into this chaotic mix of logistical improvisation and mechanical failure arrived the solution that would stabilize the entire theater: the Douglas C-47 Skytrain. To the untrained eye, it was merely a militarized version of the commercial DC-3 airliner. But when we analyze it through the lens of a systems engineer, the C-47 reveals itself not just as an aircraft, but as the perfect logistical enabler. It was the physical manifestation of the principle that in a supply chain, reliability is infinitely more valuable than complexity. The genius of the Skytrain lay in its structural redundancy and its deliberate simplicity. The airframe was built around a multi-cellular wing design. Unlike modern aircraft that rely on a single main spar where a single structural failure can be catastrophic, the C-47's wing was a honeycomb of box sections. This meant the aircraft could absorb punishment that would disintegrate other machines. Operational records from the hump are filled with accounts of C-47 seconds returning to base with half a wing sheared off by collision or enemy fire, or the fuselage riddled with shrapnel, yet still flying. From a logistics standpoint, this durability changed the math of asset attrition. A plane that returns home damaged is a repair job. A plane that crashes in the jungle is a total loss of airframe, crew, and cargo. Under the cowling sat the heart of the system: two Pratt & Whitney R-1830 twin Wasp engines. These were air-cooled radials, a critical design choice for the primitive maintenance conditions of the China-Burma-India Theater. Liquid-cooled engines, like those on the Spitfire or P-40, required complex plumbing, radiators, and coolant, all points of failure that could be pierced by a stray bullet or ruptured by vibration. The air-cooled Rhone 1830 seconds were brute force machines. They were tolerant of poor quality fuel, resistant to overheating, and arguably the most reliable reciprocating engines ever built. This reliability reduced the logistical tail required to keep them running. Mechanics spent less time diagnosing complex failures and more time turning planes around for the next sortie. We must also look at how the physical design of the aircraft directly influenced throughput efficiency. The commercial DC-3 was stripped of its soundproofing, luxury seating, and galleys. The floor was reinforced with heavy plywood and steel beams to handle the shifting weight of ammo crates and fuel drums. Crucially, the engineers cut a massive double cargo door into the rear fuselage. This seemingly minor modification was a transformative logistical feature. It allowed jeeps, artillery pieces, and large aircraft engines to be loaded directly onto the plane. It drastically cut turnaround time, the critical metric measuring how long an aircraft sits idle on the ground. In a theater where the enemy was time and weather, shaving 30 minutes off a loading cycle effectively added tons of capacity to the daily aggregate without adding a single new plane to the fleet. Perhaps the Skytrain's most significant contribution, however, was standardization. Before its dominance, the hump was flown by a zoo of different aircraft types, each requiring its own unique supply chain of gaskets, spark plugs, and tires. As the C-47 became the standard transport, the supply chain streamlined. A depot in Assam only needed to stock one type of tire, one type of oil filter, and one type of propeller. This operational homogeneity reduced the friction in the maintenance cycle. When we map the data, we see a direct correlation. As the percentage of C-47 seconds in the fleet increased, The serviceability rate, the percentage of aircraft ready to fly on any given day, climbed steadily. This aircraft was not fast. It cruised at a leisurely 160 miles per hour. It was not pressurized, forcing crews to wear bulky oxygen masks and endure freezing temperatures at 20,000 feet. It effectively had no defensive armament. Yet, it possessed the short-field performance to land on the rough, hand-cut mud runways of China, thanks to its massive, low-pressure tires and forgiving stall characteristics. It turned the terrifying geography of the Himalayas into a manageable variable. The C-47 didn't try to conquer the hump with speed or altitude. It conquered it with the relentless, plodding consistency of a factory conveyor belt. It shifted the operational paradigm from a high-risk adventure to a repeatable industrial process. Section 4. When we perform a systems autopsy on the hump airlift, we are looking at a logistical organism operating in a state of permanent cardiac arrest. The mandate from Allied High Command was absolute: maximize throughput. But when we map the operational data against the environmental reality, we see a system fighting a losing battle against the laws of physics. The core metric of the operation was net tonnage delivered. Yet, for the first 2 years, the operation was cannibalizing itself to achieve it. The primary constraint was a phenomenon we call parasitic logistical load. In a standard supply chain, the delivery vehicle consumes a negligible fraction of the cargo's value. A truck burns a tank of diesel to deliver 1,000 tanks of diesel. But on the hump, the math was inverted. Because China had no aviation fuel reserves, every C-47 taking off from India had to carry enough fuel to fly to China, offload its cargo, and fly back. Worse, it often had to offload fuel from its own tanks to top off the fighters in China, leaving just enough vapor in the lines to limp back to Assam. When we analyze the consumption charts, we find a terrifying ratio. In the early stages, the airlift was burning nearly 1 gallon of fuel for every gallon it delivered. From a pure efficiency standpoint, the system was a disaster. It was the equivalent of a bucket brigade, where half the water spills before reaching the fire. This inefficiency was compounded by the aluminum trail. This grim moniker referred to the glittering wreckage of crashed aircraft that eventually littered the jungle floor so densely that pilots could navigate by them on clear days. The attrition rate was not merely a tragedy. It was a systemic collapse of capacity. In January 1944 alone, the tonnage pushed over the hump came at the cost of 3 aircraft for every 1,000 tons delivered. If we extrapolate that attrition rate, the entire transport fleet would have effectively ceased to exist within 6 months. The cause was rarely enemy fire. It was the weather system, acting as the ultimate anti-access weapon. The route crossed the Himalayas, creating a funnel for high-velocity winds and extreme icing. A C-47, fully loaded and clawing for altitude at 16,000 feet, had zero excess energy. If a downdraft caught it, or if ice disrupted the airflow on the wings, the aircraft didn't glide, it fell. We also see a critical bottleneck in the human system. The demand for tonnage forced pilots to fly well beyond the safety limits of human endurance. Crews were flying up to 160 hours a month, nearly double the modern civilian limit in unpressurized cabins. At 20,000 feet, hypoxia was a constant, insidious threat. We see pilot logs that resemble the scrawlings of madmen, detailing hallucinations brought on by oxygen deprivation and fatigue. This degraded decision-making capability. A tired pilot forgets to switch fuel tanks. A hypoxic pilot misjudges a cloud bank for a mountain pass. The human failure rate was actually a system scheduling failure. The operational tempo was consuming the operators as fast as the machines. However, the autopsy also reveals the moment the system adapted. It wasn't a sudden breakthrough, but an accumulation of incremental efficiencies, a classic learning curve effect. The introduction of radio beacons and better meteorological forecasting reduced the navigational variance. But the real shift was the sheer industrial application of the C-47. The Allies stopped treating the hump as a series of individual heroic flights and started treating it like a railroad schedule. They saturated the airspace. By 1944, a C-47 was crossing the ridge every few minutes, 24 hours a day. When we crunch the numbers for July, 1,945, the contrast is staggering. The monthly tonnage had exploded from a paltry few hundred tons in 1942 to over 71,000 tons. The system had scaled. The C-47 seconds were now carrying trucks, mules, artillery, and entire dismantled road graders. The parasitic load had been mitigated not by changing the physics, but by optimizing the flow. They built a pipeline alongside the airfields to feed the planes faster. They improved the airfields in China to allow heavier takeoff weights for the return trip. The system's autopsy of the hump teaches us a brutal lesson about logistical velocity. The early failure wasn't because the C-47 was a bad plane. It was because the support system, the airfields, the pilot training, the weather data lagged behind the airframe's capabilities. Once the infrastructure caught up to the technology, the Skytrain ceased to be a struggling aircraft and became a dominant strategic capability. The sheer volume of C-47 seconds overwhelmed the attrition rate. They were losing planes, yes, but they were delivering victory by the ton. The aluminum trail below was the price paid for the river of supply above. It was a victory of quantity, standardization, and a rugged machine that simply refused to stop working, even when the system around it was breaking down. Section 5. When we render a final verdict on the C-47 Skytrain's performance in the China-Burma-India Theater, we are forced to redefine our understanding of air power. In the popular imagination, air power is defined by the kinetic impact of bombers, or the agility of fighters' machines, designed to destroy. But the lesson of the C-47 is that true strategic power lies in the ability to sustain. The Hump airlift proved that a reliable logistical artery, maintained through the air, could keep a nation on life support and tie down 1 million enemy troops. The data supports a clear conclusion. The C-47 was the single most valuable piece of hardware in the Allied inventory. General Dwight D. Eisenhower famously listed the C-47 as one of the 4 pillars of Allied victory, alongside the Jeep, the bazooka, and the atom bomb. This is a staggering inclusion. He placed a slow, unarmed transport plane on the same pedestal as the weapon that ended the war. Why? Because without the C-47, the logistical reach of the Allied forces would have collapsed. The Skytrain allowed commanders to decouple their strategy from the limitations of roads and rails. It turned the sky into a supply chain. The ultimate takeaway from this case study is the triumph of reliability over performance. In a sterile test environment, the C-47 was unimpressive. It was slow, it shook, and it was drafted from civilian life. But in the chaotic friction of war, it possessed the supreme quality of rugged availability. A faster plane that requires 40 hours of maintenance for every hour of flight is a liability. A cargo plane that requires a pristine concrete runway is a limitation. The C-47 worked in the mud, in the monsoon, and in the hands of exhausted mechanics. It proved that in logistics, the good enough solution that works 100% of the time is vastly superior to the perfect solution that works 80% of the time. Furthermore, the systems developed over the hump, the high-density flight corridors, the all-weather instrument flying, the cargo loading algorithms did not end with World War II. They became the blueprint for the modern world. Just 3 years after the war, when the Soviet Union blockaded Berlin, the Allies didn't panic. They simply dusted off the operational manual from the Himalayas. The Berlin airlift was the direct intellectual descendant of the hump, executed by the same planes, and often the same pilots. The C-47 didn't just save China, it validated the concept of strategic air logistics. It proved that with enough determination and the right machine, you can bypass geography entirely. History often remembers the generals who drew the lines on the map, but it rarely celebrates the systems that made those lines real. The story of the hump is a reminder that the most powerful weapon in a conflict isn't always the one that shoots. Sometimes, it's the one that delivers. It teaches us that while courage can win a battle, only a resilient, unbreakable supply chain can win a war.